Alright, time for another DraftScience video presentation. So I guess we'll talk about kinetic energy. Just because I found this sort of kinetic energy in general. I don't know. The physical universe, how does it work? Anyway, how do you convert newtons into joules? And so every single answer says you can't do it. So, and the reason is because force isn't energy. One of the answers is like a Puro special, where the asshole answering the question pretends we're talking about, like say if we were talking about a sailboat, we said, how much energy does the sailboat have when it's going 30 knots or something? And then they decide to say, well, let's figure out how much, if we burn the wood of the sailboat, how much energy that would produce. And if we nuked the sailboat, that is, we exploded every single atom in the sailboat, how much energy would we have? I mean, it's so... sorry. I mean, it's such an indignity to being reasonable or intelligent. It's just smart ass. So it's just, assholes pretending to be smart, because they know some words and some jargon. But they're obviously they don't know what logic and reason is. All right, so let's talk about newtons and force and momentum and joules. It'd be nice to talk about pounds, but we can't do that yet. Not quite. Might be the way to get there mathematically, but I just don't see it. But anyway, just relying on the blah blah, the bullshit. This is inconvenient. Oh, you may have noticed the temperature is much better. The fan wasn't working on the video card. So I put another fan in the case, and so everything's fine, graphics card wise. All right, so a newton is, I don't know why, 102 grams. So, just to make things messy. And so the idea is that it weighs 102 grams is 102 grams in weight in Earth, right? You have to be on Earth, in Earth gravity, for that standard to apply. But that's what 102 means, is that you can detect how many electrons and protons you have by detecting how much force is applied to a spring, okay, when one side of the spring can't move. Okay, so it's telling you the compression of a spring in Earth's gravity. A certain amount of electrons and protons weighs, 102 grams. So it's the same thing. You could say that, so this is falling a certain rate. It has a certain momentum that's creating this idea of its weight. Its weight is being read based on going a standard speed, which would be 1 meter, per second. So if you go 1 meter per second, that sort of figures, right? You multiply the mass times the speed, and if the speed's 1, that would be the assumption. So right now you're moving 1 meter a second down. You're also moving 1 meter a second up, but the only part that matters is the down part, in terms of your weight. Well, there's a differential, obviously, of 1 meter that the spring absorbs on the scale. So the idea is, if I took 102 grams, I took a newton of weight, of mass, of atoms, and I move it. Let's say we move it sideways instead of moving it down. Instead of worrying about what gravity's doing. Let's say we want to hit a scale, that we put horizontally, and now we want to measure. We want to get the same weight. We want this to weigh 102 grams when it hits. Well, then we would move it at 1 meter per second. So if we move 1 newton that way and throw it 1 meter a second, it'll hit the scale and read 102 grams. That's the idea. Anyway, So if we're falling at 9.8 meters, let's just make that 10, just for simplicity. Then that's the definition of a joule, is instead of going 1 meter per second, we go 10 meters per second. So now, if I move the joule 10 meters per second at the wall, okay, now what it's going to weigh, okay, I don't know, because nobody's done it. Yeah, so we don't know it for sure. But the idea would be that, it should weigh a kilogram, which doesn't make much sense, right? I mean, it should be 10 times. But, that doesn't make much sense. You drop a quarter stick of butter 1 meter, and it actually weighs 2 pounds, more than 2 pounds. That doesn't seem very realistic, so I don't think that's true. But the point is it'll weigh on a scale, okay, 1 joule's worth of energy. It'll have as momentum anyway, we could argue. I mean, you're just doing the math. You're just saying, okay, so it's it's 0.1 kilograms times the meters per second. That's what we did over here. So you'd have to say, well, that's 1, something. So it's 1 momentum anyway, and it's 1 joule. So 1 momentum equals, so your momentum, just doing your mass times your velocity, will equal joules. Technically, that would be the right definition, the correct answer, where their answer is, just incomprehensible mush, really, this whole squaring idea. That won't get you the right answer. So what else do I want to say? So yeah, so technically all we got to do is drop a pound, 1 foot. Yeah. And then that they say when you drop a pound 1 foot, that's 1.3 joules. So that's probably not I shouldn't even go there, because then we're just getting into something making it more complicated. But technically, 1 pound dropping 1 foot is the same as 102 grams dropping 1 meter. So those two are supposed to be the same thing. So the stick of butter falling a meter is supposed to be the same as a pound falling. So we know that a joule has to be more than a pound already, because 1.3, I mean, the 0.3 isn't much of a differential. So it's going to be pretty close to a pound. And so a pound is a lot less than a kilogram. So that's not going to work. So I'm just saying they're breaking the math to suit the mv squared formula, and not because it needs to be broken. I mean, these things all should be proportional, and the idea is that a force is always just stuff moving. And whether it's actually made out of tiny little bits that you can't see, or it's made out of a car, or it doesn't matter what it's made out of, whether it's made out of matter or it's made out of the force itself, it really doesn't matter, because we know it's momentum. We know it's your mass and your velocity that makes you compress a spring a certain amount. The heavier you are, and the slower you're going, versus light things going fast, and they'll compress the spring a certain amount. And that's the real argument. Now, it's just kind of glaring that none of these simple experiments are done. So the ones we don't have, that we really should have, I mean, it doesn't make any sense that where we can't say any of this for sure, because you can't find an experiment where it's actually done. I mean, I've shown ones that imply it, okay, so where they take different masses, and separate them by explosion. Okay, so you take a double mass here and a 1 mass here, and you send the same force, you apply the same force to them both, and this one goes 1/2 the velocity here of this one. This one goes 1 velocity, and this one goes 1/2 of that velocity, and it doesn't matter whether I make this, 100x, I mean, mass, I'll get a proportional reaction, and this side will always go the same speed. This one velocity will always be the same velocity, no matter what's over here. So it's like the gun. Example, if I made a gun that didn't have an end to it, right? So I just have a bullet, and I have an explosion, and I don't bother stopping the explosion from going out this end. This bullet's going to go the same speed no matter what happens here. The only thing I can change is how much the gun recoils. And the only reason why the gun would recoil is that I put some impediment in the way. If I put an impediment in the way, then that will cause the gun to recoil. But if I don't have an impediment, like a zip gun, I won't get much recoil. I mean, I get some because there's some resistance, in the gun-bullet relationship. Especially if you have the gun with grooves in it and you're going to try to spin the bullet, all of that will create some force in the opposite direction because you're applying some friction. But if there's no friction, if I make it frictionless as possible, I'm not going to get a recoil of the gun. I'm just going to get a bunch of shit coming out the end of the gun. It's like the bazooka thing, right? I mean, bazookas are manageable. You put a big shell in there, and there's a big explosion, but the bazooka lets it all shoot out this end so the guy can actually hold the damn thing and shoot a missile, and, it doesn't knock him over. Alright, so that's one way of saying it. I mean, the trick is it's hard to keep your explosive has to be built into your missile, essentially. Just because you can't, pack it in there and then, ignite it without any obstruction, without any friction. Alright, so where do we go from there? So, I mean, there's not much to say. I mean, it's there, this whole argument is about, how you've broken something simple and made it complicated. And I guess I would compare it to like bent space. I mean, this idea that you've come up with this non-mechanical, non-real thing that's causing effects in the universe. The space itself is somehow, doing it without a mechanism. There's no mechanical. That the electron sits in space and somehow it has a bent space reader. And it can tell which way the space is bent. There's no interaction with it and a force, some kind of real thing affecting it. It just somehow knows, okay, I looked at my bent space detector and it says I have to go that way. I mean, and they call this physics. This is some sort of physical explanation of reality. And that's not physical. And so again, they're saying that force, this thing that always does something, in the sense that makes something either move this way or makes it move that way. And you could kind of understand that if you have a standard amount of pressure in the universe, that is a standard density of stuff, that if you produced less density, that is if you were shooting this way with less than, only 2 elements and the average is 3 in the universe, that is the same thing. Having less force than the average force would be the same thing as an attraction, but the attraction isn't really pulling. It's just relying on the fact that there's more push than there is counter push, and that's why things move. And so the force is less than the average force. You could argue that I would say something like, I would speculate that infrared radiation is at the density of the average amount of force that gravity possesses. That gravity is at the that's why there's like sort of a distinction between radio waves and stuff on the light, higher than the light spectrum, the visible light spectrum, is because of that density issue. And so everything on the low end is clumping. Okay, the space, the thing that makes the radio wave interesting isn't the part where there's more stuff. It's the parts where there is less stuff. So, you know, if you're getting a signal, you're thinking of the signal as being more energy, but the important part is the place where there's less energy, and that's where you're less than the average density of, say, infrared light. And that would tell you that that's, you know, well, anyway, that's the less part. All right, where else do I want to go? Didn't say that exactly the way I wanted to, but anyway, get what you get. So, you know, maybe I'll pause. You know, there's not much to say. So the idea is, I'm arguing that all interactions are interactions. Basically, the only thing that makes 102 grams significant is how fast it's moving. I mean, as an energy equation or force equation, it just doesn't matter. So I have 102 grams and I move it. Like I said, I move it this way. I can move it 1 meter per second. I can move it 10 meters per second. Those two velocities will produce a different amount of impact on something. It'll hit something and it'll have more impact because it has faster speed, but it won't be squared. There's nothing, it's not some sort of super magnitude. Well, I guess that's something to go over. I mean, I could just add again the simple argument for why it matters, why speed creates an illusion. And the simple answer is that, you know, if something's going faster, then it's going to deposit its energy in less time. So you can understand that it goes from point A, it passes a given space. So this is the given space. If something's going faster, it goes through that space in less time. So that's one thing to understand. The slower thing takes more time to cover the same amount of space, to go through the space, to interact with the space. And the real key thing is when you're depositing your energy, the faster you're going, the more velocity you can give anything you hit. So it doesn't matter what you're hitting, you know, whether it's a big thing or a small thing, you can give it more velocity because you have more velocity to give it. So a light thing or heavy thing, you can give them a bigger portion of momentum per interaction because you can give them potentially more velocity. Now the big things are tricky, things bigger than you, because now it takes more time than the speed. You're going too fast and you don't have enough time to give the thing your velocity. So you're going to bounce off because it's not taking your velocity quick enough. It can't absorb it as quickly as you can deliver it. So it's going to get rejected for that reason. But all the small things, okay, you can make them go your velocity. So everything leaves at your velocity. You can give them, if you're going 30 miles an hour, you can give them 30 miles an hour. So you're able to give them a full portion of velocity. So every little thing you hit, it leaves at the same velocity you're going, minus how much you had to give, you know, how much, the percentage of your mass they are. If they're 1% of your mass, then you'll lose 1% of your energy with each interaction, but each one of them will be going 30 miles an hour. And the tendency is for fast things, because they're interacting quickly, and they can give that full velocity, the tendency is that the energy keeps going in the same direction that you're going. Where if you're moving slowly, okay, then you're not going to be able to change the vector. Say if something's moving this way at, you know, some speed, some little thing is moving this way at some speed. If you're going faster than the speed it's moving, then obviously the new vector is going to just be bent a little if you're going much faster. So the faster you're going, the more likely, whatever direction, I guess I should draw that better, because it's really an important difference between slow things and fast things, is assuming, so you already know that everything already has a temperature, right? So we're not hitting things that are super cooled. We're hitting things that where we know internally the bits inside are already moving. So they already have a vector in some direction. The little atoms, everything's moving, Brownian motion, however you want to describe it. So they all have a vector. So when you're adding the energy this way, if your energy is, more, 2x, 5x, let's just say 5 times faster than the movement of the atoms, you could sort of understand that when the atom moves this way and I hit it, these two vectors will now add up to something more straight. And so the slower I'm going, the more the motion of the atoms matter, and the faster I'm going, the less they matter. The less they're going to affect the direction of the energy. So, and again, what happens if I hit something and I move it in the same direction I'm moving? Well, it's essentially going to do my work for me. It's going to go forward to me and hit something and make it go forward. So I didn't lose the energy. So I transferred it to this, but I didn't lose it because this thing I transferred it to is now going to do the same work I would have had to do. And so now I'm not going to have to do the work. I won't have to hit this thing to make it move because this one will do it for me, in a sense. And so that the motion all stays on this line. So that's why fast things look like they do more work, is because they penetrate better because the energy stays in the direction you're moving. Where slower things, the energy ends up going in these other directions, and that's like friction, that's heat. When you're letting when you shoot something in and it starts moving things in the wrong direction, that's what throws everything off. So that's what happens in clay. So when something slow goes into clay, the clay molecules are moving in directions, and that's what's happening basically, is their direction has more influence. So the slow moving thing ends up getting bent. Chalk dispenser. I have to get a new piece of chalk or put some tape on it or something. Anyway, and so it ends up, a lot of the energy ends up going in these tangential directions, where the faster you're going, then you're going to hit the clay molecule and it's going to keep on the same line, generally speaking, that you're going, and so the energy is going to keep going in that direction instead of going in these directions. And so that's why fast things penetrate clay better than slow things. They have a huge advantage in terms of how far they penetrate, because the energy they're giving stays in the direction that the energy is going, rather than moving stuff this way and this way, allowing stuff to go this way and that way, I guess another way to say it. Alright. But I mean, just every single comment is this line. A joule is a unit of energy and a newton is a unit of force. That somehow you could make a distinction between force and energy. And, you know, again, this goes back to Newton in the sense that Newton told you basically that force equals momentum, and momentum essentially equals weight. So it's all the same thing. The part of the force that's going to make you move, it has a certain amount of momentum in it, and it just transferred the momentum to you. So when the bowling ball hits a bowling pin, it's transferring its momentum, something it has, a quantity it possesses, and it gives a piece of it to the pin, the first pin it hits. And then the next pin it hits, it gives another portion. As it gives its portions away, it's losing its energy, and it's losing its ability to force pins to move. I mean, you know, you can't call the moving bowling ball something other than a force. You know, it is a force. It's going to hit things and do what forces do, which is move the objects. And it's going to move them because the bowling ball has force. And it's just basically going to transfer what it has to the other objects. And it only has so much to transfer. And once it's transferred, once it's caused a mass equal to its own to move a velocity equal to its own, then it's going to stop. That's not, you know. Alright, that's enough, probably. I'll pause and think about it, but you know, I mean, it's no point. There's no rational counter arguments here, so there's just nothing to argue. They don't have a defense for this mush. Alright, I probably should have just gave the simple answer to the questions. I mean, how to convert newtons into joules? A joule would be the weight of a kilogram. and a newton is the weight of 1/10 of a kilogram. So, yeah, there's 10 newtons in a joule. Logically, you would argue that would have to be how it works out. So the simple answer would be you just multiply by 10. Yeah. It's really how it has to work out, right? So 1 kilogram going 1 meter per second weighs the same as a newton going 10 meters per second. But I don't think it works out that way, frankly. So that's why I think you really have to weigh them. I mean, there's intrinsically something wrong with the idea, just because I think the 1 is the real problem, right? I mean, you can multiply something by 1, whole number 1, and you get no improvement. You add nothing, is the point, right? So if I have a mass of a certain amount and I multiply it by 1, I'm not getting anything extra. My 1 doesn't equal any change in the number, and frankly it should. Unless you want to accept this idea that we're constantly moving 1 meter per second, even though there's no visible evidence that we're moving 1 meter per second. So anyway, that's where, I guess moving and weighing everything is motion is all we really need. These experiments of just moving, swinging on a pendulum, however you want to do it, moving the weight at a specific velocity and then measuring how much it dents a scale, and that'll tell you the weight of the energy. And then, you can verify one way or the other. It's just hard to believe that a kilogram, the weight of a kilogram, is, well, no, that makes sense, right? That 10 newtons, 10 sticks of butter would equal a kilogram. So it would be 2 pounds plus some extra. So I guess in some sense it does work. But anyway, it's just convoluted. I'm just going by the idea that if you take a human being and he jumps 1 meter in gravity, so he's going 10 meters per second when he hits the ground. The idea is that that person would weigh 3 times, somewhere around there, 3 times their weight. Not that they would weigh 10 times their weight. I mean, they weigh a certain amount before they jump. Before they jump, they're going 1 meter per second. So they should weigh 10 times that amount if they drop the 1 meter. And that's no chance. So there's something wrong. Anyway, it doesn't matter. I mean, it matters, but it's just pointing out how these units are just fundamentally irrational. I mean, even the idea of why they 102 grams, why would they do that? It's just, they should have made it 100, of course, but why would they define a newton as that quantity? Is just so useless. So anyway, so I will call it a video, but it wasn't much of one. So, but there's not much to argue. I mean, there's no reasonable counter argument. So, can't really argue the non-existent counter argument. So this has been a DraftScience video presentation and such, so forth and whatnot.